multiple ways that you can actually measure the angles, or measure the degree, measure an angle. How about that? Using degrees, which we are used to. And then there's another one that is called a radian. So that's what we're going to be talking about to start off today's lesson. And some of you might have jumped ahead a little bit in terms of the assignment and started working with the math in the radians, which isn't actually all that complicated, but we need to know what a radian is. And so we are going to start off here with, what does this say? We're going to develop a conjecture regarding the ratio that measures the radius and arc length of the same angle. So we'll talk about arc length today as well. We haven't really mentioned that at all yet. We didn't talk about that at all yesterday, but let's just go ahead and start here. You can use the sketch below to explore the relationships between arc lengths. So like how much of the circumference it takes up, the actual distance between the 2 points. And then the radius of the circle. So for the first measurement, we're just going to use this up here. And the length, the L is for the arc length, which tells you that it is 5.05. So we're just going to write 5.05. And we're going to write the radius, which happens to be, looks like 3.62. And then you're going to divide 5.05 by 3.62 to figure out the ratio between those two. So I want you to go ahead and do that real quick. And I'm going to get something else set up here. So go and do that calculation real quick and then write in the answer to that. Anybody have an answer for it? 5.05 divided by 3.62. Yeah, it's about 1.4, right? So yeah, just type there, write in 1.4. And what I'm doing is I'm bringing up the digital version of that so we can actually change the measure and do a couple more measurements here. So a few more seconds and we'll get things going. Let's do 2 more. There we go. All right. We're going to get 2 more measurements because it says there's 3 measurements here for the first one. The first measurement is just the one that's built in, this one here. But in order to get more measurements, we actually have to change things. So let's make this one a little bit smaller. So the length this time, so in our measurement, second measurement, write in 2.79 for the length. And write in 2 for the radius. And then do the division, what do you get? 1.4, all right. And then for the third measurement, you probably at this point know what the division is going to equal, right? What's the division going to equal? Probably going to be 1.4. So let's say length of 7.38 with a radius of 5.28. And do the division, what do you get? 1.4, all right. So we're talking about proportions. So much of what we do here is proportional, which makes sense because every circle is proportional to every other circle. So describe the relationship between the value. It's a constant relationship. It's 1.4. So we don't need to write that. We can just talk about it. That's fine. Question 2A, as the size of the circle changes, what happens to the ratio of L and R? Yeah, stays the same, exactly. That ratio doesn't change, it stays exactly the same. Let's see, make a conjecture about the arc, the length of the arc intersected by a given central angle and the radius of that circle, of the circle that contains the arc. So arc length and the radius. Well, it's always going to be the same, right? So that's what we'd have for 2B. Based on your conjecture and exercise 2, what does the radian measure of the central angle represent? So, by the way, radian is an interesting bug. It's like red. A radian is given by this symbol here. So this symbol represents the radian, and this symbol is known as, we call this theta. It's a Greek letter, Theta, theta. Theta, and we use this for radians. So instead of using the degree symbol for measuring an angle with degrees, we use the radian symbol, theta, for measuring radians. So based on the conjecture in exercise 2, which we just said, it's always going to be the same. What does the radian measure of the central angle represent? So the radian is equal to, you ready for this? It's equal to the arc length divided by the radius. Arc length divided by radius is a radian. What's that? It did pass out a new paper, yeah. Who needs that one? Oh, Yvonne needs it, and Katie. Okay, cool. There will not be a unit test, there will be a quiz. Next week, probably Tuesday. Okay, Tuesday or Wednesday. Yeah. All right, so theta, or not theta, but a radian is equal to the arc length divided by the radius of the circle. So this is called theta, Theta. It's a theta, yeah, it's a Greek letter. I mean, pi is also a Greek letter. That symbol for pi, it's a Greek letter. This one, theta, is a Greek letter as well. We use this to measure radians. So instead of using the degree symbol for degrees, this is another way of measuring angles, but we use this symbol instead. We don't put it up to the right like we do a degree symbol. And the degree symbol, yeah, theta represents radians, degrees represents degrees. So it's a different unit of measurement for the same thing. So they're both measuring angles, but one's radians, the other's degrees. Yeah, it's like centimeters versus lengths. Cool. Down here, radius. Yeah, arc length divided by radius. All right, flip it over. So next question, number 4 on the back. What causes the length of AB? What causes the length of arc AB to be proportional to the radius? Listen up. What causes the length of arc AB to be proportional to the radius? What's that? I mean, it's kind of a mixture of that, yeah. Oh, we already have the equation, L over R for that next one. What's that? Yeah. Yeah, what causes it to be proportional to the radius? Yeah. Similar? Yeah. Yeah, because it has to do with similarity. Yeah. That's essentially. What's that? Yeah. It's proportional because all circles are similar, right? If you grow the circle or you shrink the circle, every circle is similar to every other circle. Therefore, the length of AB would have to have that constant proportion between the radius because they're growing and shrinking at the same rate, and every circle is similar to every other circle. Therefore, that relationship isn't going to change. Yeah, basically. We don't need to write that down, but it's just an explanation. Yeah, because all circles are similar, basically, would be a nice, concise answer for that. And in terms of the what is this? Equation, yeah, that's just going to be arc length over radius. And you can just write L over R, L for arc length and R for radius. So when an equation to show the relationship, or write an equation to show the relationship between the radian measure of a central angle, the length of an arc, and the radius of the circle, represent the radian measure with theta. Theta is often a variable that we use as well, just to say, hey, this is an unknown angle measure. Instead of x, sometimes you'll see theta instead of x. It can be used as a variable, but specifically in degree, or not degree, specifically in angle measures, it's used to talk about radians. All right, that's it for the warm-up. I just kind of wanted to give you an idea about what a radian is. And a radian is just the arc length divided by the radius. That's how that measurement was come up with. So let's go ahead and get our notes back open. We need to finish up the lesson from yesterday. We're on lesson 10-2. Those do not need to be kept. No. It's kind of like the ones where we do online sometimes. We don't really hang on to those, but just something to see, something interesting, something good. All right. So today we're going to be talking about the lengths of arcs. Listen up. We're going to finish the lesson from yesterday. Second part of the lesson has to do with the length of an arc, how far around the circle it is, and the measure in radians versus degrees. Yeah. For today, yeah. Okay. All right. So let's get our books open, please. Books open to page 580. 580. Abby, do you have your book? Page 580. 580. 580. So we're talking about arc length. How long is that section around the circle between the 2 points? And we're talking about radian measure as well. So we're going to be talking about degrees like we talked about yesterday, the measure of an arc in terms of degrees. We're going to be talking about the length of an arc, and we're going to introduce radian measure as well. So arc length is the distance between the endpoints of an arc measured along the arc in linear units. Linear units meaning as if it was a straight line. Even though it's a curved line, we're treating it as if it was a straight line in terms of the distance. Because an arc is a portion of a circle, its length is equal to the fraction of the circumference. So let's say, for example, that, I'll just do a quick example on the back of the warm-up here. You don't need to write this down. But if you have a circle, and the circumference is a nice whole number like 4, and you are measuring the distance from A to B, and AB happens to be a semicircle. How much of a circle is a semicircle? Half. So the distance between A and B would be what? 2. Yeah, because all the way around is 4. So halfway around would be 2, because 2 is half of 4. If it took up, let's say, let's put C here. That's a 90-degree angle in the middle now. What's the distance between C and B? 1, yeah. Because 90 degrees is a fourth of a circle. If the entire circle all the way around it is 4, then a fourth of the way across it would be 1. So that's how we're going to be dealing with this. Now it's going to be a little bit, not quite that straightforward, but the basis of it is that. So we do have an equation that we're going to be talking about here. And so in words, we're talking about arc length. First of all, we're going to talk about it in degrees, and then we'll talk about it in radians after that. So we'll start with degrees, and then we'll talk about radians. So the ratio of the length of an arc, L, to the circumference of a circle is equal to the ratio of the degree measure of the arc to 360 degrees. All that is saying is the length that you have, first of all, the length out of the circumference. This is the formula for circumference, right? 2 pi r. So the length out of the entire circumference is the same as how many degrees out of 360 you have. Okay, so if you're talking about like all the way around a circle, that's 2 pi r. If you're talking about halfway around a circle, that would be pi r, right? Because that would be half of 2. If you're talking about half of 360, that would be 180. So if we're talking about equivalent numbers here, if we're talking about half, this would be pi r, this would be 180, because each of those things would be half of those. And in terms of the actual formula that we're going to use, it's right here. The equation to figure out is the circumference, 2 pi r, times the fraction of 360. We just said that if this right here, the circumference is 4, and we're using 180 degrees, 180 out of 360 is equal to what fraction? So what if this was 180? What fraction would that be? 1/2, yeah. Half of 360 is 180. So 180 out of 360 is the fraction of 1/2. Times the circumference, which in the example I gave is 4. 1/2 times the circumference of 4 is 2. That's why the argument is 2. So this right here gives you a percentage of 360. If this is 90, 90 is 1/4 of 360, which would be 0.25 or 25% of the distance around the circle. If it's 36 degrees, 36 would be 1/10, which would be 10% the way around. So you're basically just getting a percentage from this number, and then you multiply it by the distance around it. So it'd be like 10% of the circumference or 25% of the circumference. So you're just talking about different fractions, different percentages of the distance around a particular circle. The only thing you need to solve this is a radius, r, and an angle measurement, x. Those are the two parts that you need to solve this. You plug those two in, and you can get your answer. Now, angles can also be measured in radians. And a radian is a unit of angular measurement equal to 180 degrees divided by pi. So a single radian is equal to 180 over pi, which is roughly, if you type that into your calculator, 180 divided by pi, that's about 57.296 degrees. So it's kind of like converting between inches and centimeters. It's not, you know, they obviously don't line up perfectly because it's a different unit of measurement. But right here, it says that the radian measure of a central angle is the ratio of the arc length to the radius of the circle. That's what we just did in the warm-up. So whatever your arc length is, divided by the radius, gives you the radian measure. Whatever the radian measure is going to be that ratio. So let's continue, and we'll do a little bit of work with this. And the more we do this, the better it will get. Because we haven't actually done any math with this stuff yet. So you are going to learn how to convert, first of all, between degrees and radians and between radians and degrees. You probably converted between different types of temperature, Celsius and Fahrenheit. You probably converted between inches and centimeters. You probably converted between meters and yards and all that kind of stuff. So this is a very similar process. It just has a quick formula, and that's how we're going to deal with it. So to convert a degree measure to radians, you're going to multiply by pi over 180. And then, so if you have let's say you have 180 degrees, and you want to convert that to radians. 180 degrees to radians. And we can abbreviate that as rads for radians. We would take 180 and we'd multiply that by pi over 180. Now, if you do that, you're going to end up with 180 pi over 180. So really the 180s cancel out, which means pi radians, or about 3.14 radians. So 180 degrees is half of a circle, which means that in radians, half of a circle is equal to pi amount of radians, or about 3.14 radians. You can do this the other way around. If you have pi radians to degrees, you would take pi, and then you would multiply that right over here by 180 over pi. So you multiply that by 180 over pi. And in this case, the pi's would cancel out. And you get 180 degrees. So those two things are equivalent. 180 degrees and pi radians are the same thing. So if we're talking about radians and you say pi, you're talking about half a circle. So that means all the way around a circle would be 2 of those in radians, which would be 2 pi. So the entire circle in radians is 2 pi. The entire circle in degrees is 360. So 360 degrees is equal to 2 pi radians. And then you can just figure out whatever you want in between that with these 2 short conversions. And that's what we're going to be dealing with a lot today. So let's do an example. And then if you have questions after that, feel free to start asking. But there's not a whole lot more work for us to do until we actually are just done with this lesson. So let's have a look. So you're going to find the length of AB to the nearest 100. And we're using degrees here. So we're going to find the length of AB to the nearest 100. So we're trying to figure out AB. AB is right here. It's the distance between those 2 points. That measurement right there is the diameter. I just want to be clear about that. That is the diameter. So that means that the radius is equal to 7. Now, you could use 2 pi r. I wouldn't actually recommend using 2 pi r here because we actually have another one for circumference, and that is just pi times the diameter, which is what I'd recommend doing on this one. Because we have the diameter, we may as well use the circumference formula that uses diameter. So the formula that we're using is arc length is equal to x, which is the degree measure, out of 360 multiplied by the circumference. And the degrees that we're using are 80, because that's how many degrees there are between A and B. The measure of arc AB is 80 degrees. And then here, we're going to say 14 pi. Because we're using pi times diameter instead of 2 pi r. And so all you'll need to do now is multiply on your calculator 80 over 360 times 14 pi. And whatever that is your answer. So, you can grab a calculator here. So 80 out of 360 times 14 pi. So the length of that arc is about 9.77 meters. That's what we get. .77. Now, I'm going to break this down a little bit more, at least for this first problem, because I do want to show you exactly what's happening with all these calculations. So if we're talking about the circumference entirely, the circumference is 14 pi, which is about 43.98 meters, okay? So C, circumference is about 43.98 meters. Now, out of that 43.98, the length of AB is 9.77 of that amount. And so this part here, the 80 over 360, is giving us the percentage out of 360 degrees. So if you take 80 and you divide it by 360, that gives you 22.2 or 0.222, which is equal to 22.2%. So that means that AB, the length of AB, is about 22% of the entire circumference. So if you take this number here and you multiply it by 0.222, you should get a number that's very, very close to 9.77. So 43.98 times 0.222 and 9.763, which is about 9.77. And the reason why it's not exactly the same is because we rounded and estimated with those numbers. But that's what we're dealing with here. Figure out the circumference, figure out the percent that the angles take up of the entire circle, multiply them together. That's what the formula is, and it gives you the answer. So let's try the check step here. This time we should be using 2 pi r instead of pi times diameter. So let's write it out. We're going to say L is equal to, what number goes over 360 on this problem? 45, okay. 45 over 360 multiplied by 2 times pi times the radius, which is, what's the radius this time? 3. This can be typed directly into your calculator, just like that. You don't even have to do the 2 times 3 to get 6 pi if you don't want to. So we'll get ourselves a fraction. We'll type in 45 out of 360, which is actually equal to 1/8. And then we're going to multiply that by 6 pi, or 2 times pi times 3, however you want to do that, to the nearest hundredth. What is the answer to the nearest hundredth? Is it 2.35? .36. Good. All right. 2.36. Always look at the number after the number you're rounding to. If it's 5 or more, that rounds the number up. If it's 4 or less, keep that number the same. But since that 6 is more than 5, this 5 goes up to 6. Yeah. Any questions on figuring out arc length? You just take your 2 numbers, throw them into the formula, type it into a calculator, get your answer. All right. Next question. We are going to do some conversions. We're going to convert from degrees to radians, and then we're going to convert from radians to degrees. And then there's a couple more problems after that, and then we're done. So here we go. Write 135 degrees in radians as a multiple of pi. What that means is leave pi as pi. Don't write it in decimal form. So multiple of pi just means you're basically treating pi like a variable. So 135 degrees, we're going to use the conversion of degrees to radians, which is this one right down here. So you're going to multiply by pi over 180. So here it is. 135 times pi over 180. And if you do that multiplication, that gives you 135 pi over 180. 135 is the numerator, multiplied by the numerator. 135 times pi is 135 pi. 135 over 180 is the fraction that you're dealing with. And so if you type that into your calculator, you can just type in, I don't know if it'll give you the exact answer. If you type in 135 pi over 180, it'll probably give you a decimal, I would imagine. Does it do that? Double check it here. Let's see. 135 pi over 180. Oh, no, it doesn't. Nice. It gives it an exact form, which is great. That's what we want, 3 pi over 4. So it puts it in terms of pi, which is exactly what we want. Essentially, if it tells you to write it as a multiple of pi, you're basically using pi like you would use x, essentially using it like a variable. So 3 pi over 4 is the answer for this one here, because 135 out of 180 is 3/4, and you just keep pi as pi. So let's try this one. So we're going to have 240. And if you want, you can write 240 over 1, just to help you out with the multiplication, times pi over 180. So we're going to multiply by pi over 180, which equals 240 pi over 180. So that would be 4 pi over 3. Is that what that turns into? 4 pi over 3? Yeah. What's that? So this is just you can write it like this if you want to. The reason why I wrote it like this is just to remind people that when you're multiplying, you go straight across the top, straight across the bottom. So if you don't want to, if you just want to write it as a whole number, that's fine. It would be the same thing as just writing 240 times pi over 180, but just as a reminder on the rules, the whole number always multiplies by the numerator. But if you want to, so you don't have to write this one as a fraction, but you can just by putting a 1 underneath it. So yeah, that's optional. So you get 4 pi over 3 radians. All right. Now, moving the opposite direction, we're going to go from radians to degrees. And so we're just going to flip that fraction over, and we're going to multiply by 180 over pi instead of by pi over 180. So the first example we have is 11 pi over 6 radians. And the math you're going to do here is 11 pi over 6 times 180 over pi. And I don't recommend writing the word radians in the problem as you're doing this. It's best just to leave the word radians out of it, leave degrees out of it as well until you're done with the problem. But as you go through this, you're going to end up with, I'm just going to rewrite this here. I'll rewrite this down here just to kind of show you what's happening. I would write 11 pi over 6 times 180 over pi, like that, which ends up equaling 1,980 pi over 6 pi. The reason why this fraction doesn't include pi is because we have a pi here and a pi here. They're both factors of that fraction, which just means they cancel. For sure, yeah. Yeah, if you know that the pi is going to cancel out on the numerator and denominator, you're welcome to do that right away. And then 1980 divided by 6 is that 330. That's where we get that from. So, right there. So try converting 2 pi over 3 radians into degrees. There we are. Scissors. All right. Convert 2 pi over 3 radians into degrees. Should be less than 180 for sure. Yeah. 120? Yeah. So we're going to do, what is this? 2 pi over 3 times 180 over pi. Now, if you are pretty proficient with cross-canceling, this process can be even quicker. Because with multiplication, as long as you have factors that you can cancel out on the numerator and denominator, you can just start by doing that. So like those cancel out. And then 3 and 180 are both divisible by 3. So that'll turn into a 1. This will turn into a 60. And then 60 times 2 is 120. So the answer is 120 degrees. You could also just put it in the calculator and it's still 120. Yeah. So, any questions on conversions between degrees, radians, radians, degrees? Just make sure you use the right version of that fraction. Otherwise, it's not going to work. Okay. Last page. Let's keep going. And then you're going to have a lot of work time today, which is good. All right, example 8. Finding arc length by using radian measure. So now, oh, by the way, we have a formula for arc length in degrees, but we don't have a formula for arc length in radians. We have a formula for radians, but we don't have a formula for L. So let's talk about this for a second. Let's develop a quick little formula. That way it'll be a little bit easier than what they're having us do here. So if theta over 1 is equal to L over R, we want to get L by itself. Because if we want arc length, that means that L has to be by itself. This is a proportion. How do we solve proportions? Cross multiply. So if we multiply 1 times L, we get L. And if you multiply theta times R, you get theta times R. So the measure of the angle in radians times the radius is equal to the arc length. So that's the angle measure in radians. Multiplied by the radius is equal to the arc length. So we can actually do it quicker than what they have here because they're plugging in and doing like algebra the whole way through. Whereas for us, we can just plug in here now and say 9 times 3 pi over 4, which is exactly what they ended up with here. But they had to do cross multiplication and all that kind of annoying stuff. So let's not do that. Let's just use this formula instead. And we can start right away by saying L is equal to 3 pi over 4 times 9. And then we're going to approximate our answer. It says to round it to the nearest 100. So we're going to end up with 27 pi over 4, which is about what? What's our approximate length? What's that? 21.2. What's the number after it? What's that? 0? 21.20? 21? 21.21? Okay, because the number after the 0 is more than 5. Okay, or 5 or more. All right, so 21.21. Nice. Studies that the length of arc ZY is about 21.21 centimeters. Cool. All right, I want you to answer that last one on your own. Just use this formula here. Length is equal to the measure in radians times the radius. It'll make your life a little bit quicker and easier. Take a minute on that. So in inches, what is the approximate length of arc MN? Yeah, about 3.67. Good. So we're gonna have 2 times 7 pi over 12, which is 7 pi over 6, which is about 3.67. All right. That's all I got for you in terms of notes for this lesson. Before we start working though,